She's going to talk about smoothness of finite depth foliations, part 1. Please, Rachel.
And thank you very much to the organizers for the invitation and also for making the conference accessible to those of us who would not have been able to attend. This is part 1, and Larry will be giving a part 2 talk. And I'd also like to thank the generosity of John and Larry who invited me onto this project. And also, I will have a lot of pictures, and the ones I've drawn, you'll see, I'm not really the artist. The good pictures are thanks to another co-author of mine, Charles Dellman. So part 1, I'm going to be telling the C0 story in preparation for Larry Conlon's talk, where he will be talking about the smooth refinement. And so most of my talk is going to be expository, talking about the results of other people, hopefully giving the various definitions and constructions that Larry needs. So our world is going to be the world of 3 manifolds. And at the beginning, just to simplify statements, I'm going to assume that my manifold is closed and connected. I can always, there's uniqueness of smooth structures, so I can assume that it's smooth without losing anything. Also, oriented is not such a big deal, but we'll assume oriented. And we'll be thinking about codimension 1 foliations. So we'll be thinking about decompositions of our manifolds into surfaces, and they're going to be co-oriented. So if we look at the local charts where we just see horizontal planes, I can think about the planes are compatibly oriented. So let's say plus is facing up, those will be all the plus, or ambient world is oriented. Equivalently, I might talk about the co-orientation, which I can think about as being given locally by just del del Z. I'll only be caring about things up to isotopy. So I'm going to assume that I've applied a result of Caligari, which tells me that I can isotope my foliation so that the leaves are smoothly immersed, and the tangent plane field is defined and continuous. So a warm-up, which I first saw when I was learning about such things in a book by Ector and Hirsch. If I'm thinking about foliations of the torus, I've got this dichotomy. I can either think about, I either have a suspension lamination, so I can think about, I've got some choice of parameterization of my torus. So if I think about the cylinder, cutting it open along some circle, and the cylinder, I've got a foliation by vertical segments, and then I just glue by some homeomorphism, and the foliation I get is the foliation obtained by gluing those vertical segments together. The other possibility is that there's a Rabe annulus. And luckily there have been a lot of talk about Rabe things. So this is a baby example, but we have these 2 circles, and then we have a circle's worth of lines. And here's a very bad attempt at a picture over here. And because it's co-oriented, we're going to see an even number of Rabe annuli if we see 1 annulus. Sullivan introduced a variety of notions of taut that he proved were equivalent when C2. We're going to just be thinking topologically. So I'm going to think about F is taut if for every leaf you can find a simple transversal, transversal to the foliation that meets the leaf. And since we only care up to isotopy, this is equivalent to, for every point in my manifold, I can find a loop that's transverse to the foliation and that passes through this point. And I think Larry will say more about this, but that's equivalent, thanks to Sue Goodman, to no dead-end components. And often we can, well, in this talk anyway, we can just assume no essential tori, and then F is taut if and only if it has no Rabe component. So one of those foliations of the solid torus where you have a torus leaf and then an S1's worth of R2s. So there are a variety of proofs showing that every three manifold contains a co-oriented foliation. And underlying this is that, remember, we're in the world of closed at the moment, so the characteristic of my manifold is 0. But if you add the condition of tautness, you get something that is giving you topological information about the manifold. So if we have a taut foliation, Rosenberg tells us that a manifold is irreducible, Novikov that the fundamental group is infinite, that transversals are going to give you infinite order elements, universal cover is R3. Thurston tells us that if a surface is a compact leaf of a taut foliation, then it's minimal genus in its homology class. And now I'm going to much too quickly introduce the idea of an L space, which was given by Oswald and Szabo in the context of their Heegard floor theory. And also actually by Mufke and Kronheimer in the monoval floor homology. That it's an L space if it's the simplest possible in the Heegard floor sense. So there are these Heegard floor groups. One of the flavors is HF hat. So something's an L space if it's a rational homology sphere, and the rank of the hat version of M is just the order of the integral first homology. So roughly you can think about M has the Heegard floor groups of a lens space, although there are many more examples besides lens spaces. So Ajdath and Szabo in the smooth setting showed that if you have a foliation, then you definitely are not an L space. The foliation gives you an interesting contact class. And then Bodin and Kazez and I showed that you could extend this to the non-smooth situation. And sorry, here I thought I had caught my various abbreviations, but clearly last night I didn't. So sorry, Larry. So here are various things that are known. So the sort of most general result is due to Gabai, and is the one we're going to come back and talk more about. But if your manifold is irreducible and not a rational homology sphere, then one knows that M contains a taut foliation. So CTF, there's just some disagreement about whether you should put whether taut means co-oriented in taut or whether it means taut. So CTF just stands for co-oriented taut foliation. And there's a whole bunch of examples of various constructions. If M is geometric but not hyperbolic, here I have LO. So if I jump further down and I look at, let's look at the fourth bullet point. When you're a three manifold, so LO stands for the fact that the fundamental group is left orderable, which means you can put a group invariant left ordering on the group. And when you're a three manifold, the fundamental group is left orderable if and only if it acts non-trivially on R. And you can think of either of the two definitions of non-trivially on R. So there's this conjecture, I guess I might as well jump right down to the bottom, that if M is irreducible, then these three things are going to be equivalent. Not an L space. So if there's a taut foliation, you know you're not an L space. So really this leftmost if and only if is the not an L space implies there's a taut foliation piece. Lots of partial evidence for, but no real ideas, I think, about how to prove. And then the second one is really this should be, you could think about, often people draw it as a triangle. With NLS, there exists a taut foliation and left orderable the vertices of the triangle. Tao Li, Sarah Rasmussen and Tao Li have a nice recent result that the fundamental group acts non-trivially on R tells you have a taut foliation in the situation that you're a genus 2, irreducible Heegard genus 2 three manifold. But the usual fact that genus 2 is much easier to work with than higher genus. So various things are very nice, maybe can generalize, maybe can't. So foliations give you nice topological information about your three manifold. And so a question that is interesting and recently motivated, interesting by the Higot-Floor motivation, is whether three manifolds contain taut foliations. And the answer is known in geometric but not hyperbolic. So the question is asked in the hyperbolic world. So in particular, there are no essential tori. And another question is, well, do they contain C infinity foliations? Certain things Larry has convinced me are much nicer when you have C infinity, C2, maybe even C1. And it's even open whether the answers to 1 and 2 are the same. Okay, so now I want to turn the talk to focus on this Gabay result. That if you have an irreducible three manifold that has interesting homology, then we're going to have a taut foliation. And today's focus in particular is going to be on finite depth foliations. So I can think a foliation is finite depth. Well, let's think about the leaves of the foliation. So a leaf is depth 0 just means that it's compact. And a depth, it's depth k if you look at its closure minus L, and you just see a union of leaves that are of depth at most k minus 1, and contains a leaf that is depth k minus 1. And it's finite depth if there's some k, so that all leaves are of depth at most k. And jumping down a dimension, we have an easy example. If we thought about foliating the torus as just a union of two ray annuli, each simple closed curve is depth 0, and each copy of R is going to be depth 1. And in a certain sense, this really simple example captures quite a lot. Okay, so even when I try to draw a ray annulus, I run into trouble. So we would like to have some nice compact way to capture objects which are typically non-compact. And when we're thinking about codimension 1 in dimension 3, branch surfaces are a really useful tool. And a branch surface is just a compact space that is locally modeled as follows. So every point has a little neighborhood that either looks like a plane, or it looks like two planes meeting up, or it has a little neighborhood where it looks like three planes are meeting up. So a surface neighborhood, a double point neighborhood, or a triple point neighborhood. And one dimension lower, we have things that are called train tracks, like this picture on the right, where we have points that either look like one manifold points or look like double points, points where two lines come in together. Now, the way we use branch surfaces to talk about foliations is as follows. If I take any one of those three little local, I can think about taking a regular neighborhood of branched surface embedded in a three manifold. If I want to, I can, and typically I do, I can think about that branch surface as being smoothly embedded. And I can think about taking a regular neighborhood of this branch surface. And we want to think about this regular neighborhood as being I-fibered in the sense shown in the picture. So I've included a picture around the triple point, but you can imagine if you just had a plane point, you're just thinking about the little patch of plane cross I. If you had a double point, you can think about just lopping off that third piece in this picture. And you can think about if you collapse along I fibers, you are going to get back, some version of your branch surface. And the key thing I want to point out here is that the boundary of the complement, the boundary of the neighborhood of the branch surface, naturally decomposes into horizontal boundary and vertical boundary. So the vertical boundary is the boundary which is a union of I fibers, and the horizontal boundary is what's left over, or the part of the boundary that is transverse to the I fibers. And the game when you have a foliation is to Danjois split along a leaf and then isotope your foliation so that it lies in one of these neighborhoods everywhere transverse to the I fibering. So the original Danjois splitting happened when thinking about the torus. And so you're just saying, oh, okay, let's think about how any orbit, any leaf intersects, let's say that the circle cross zero, and you can think about blowing up the intersection points with the leaf or the orbits into little intervals, and you need to exponentially damp them so there's enough space in your manifold. And Danjois blow up is just to, I guess Danjois splitting is just to do this blow up operation and then remove the L cross open interval 0, 1. So you have a leaf of a foliation. Locally, that's just a plane. So locally, the picture is really easy to understand. You just take the plane, you replace it by the plane cross I, and then you remove the L cross open interval, and you're left with 2 copies of your leaf. You've created space in your manifold. And then again, in 3 manifolds, if you choose your plaques carefully enough and your description carefully enough, you can again, start, say, with a plaque. You've got you want the sum of the intervals, that infinite sum, presuming you've got countably infinite intersections to be finite, and then you just have to make sure everything matches up. So the Danjois game in the torus just generalizes very naturally. And so again, foliation, you split open along a leaf, and then you have some space in your manifold. You sort of push the leaves so that they lie in the neighborhood of the branch surface everywhere transverse to the I fibers. And I give you a foliation. You can always find a branch surface so that the foliation is fully carried by the branch surface. The game is thinking about triangulations of the manifold and Hawken normal form. And there's a result of Gabai that says there's actually finitely many branch surfaces that carry all possible taut foliations. So any foliation is carried by a branch surface. And as we're restricting attention now to taut foliations, there are finitely many branch surfaces that carry all. Okay, so Gabai's game was to notice. So actually there are 2 versions of Gabai's game. He had a trilogy in JDG, and I think of one version as the version where you look at a hierarchy. For people who know the various constructions, everyone else can ignore the next minute. There's one construction where you look at a hierarchy, look at the union of bolts, foliate those, and then pull the foliation back. The other is a forward construction that he gives in the 3rd article, and that's the one I'm going to be describing here. So let's first remind ourselves, let's go back to some classical topology. And we can think about, if I have a 3 manifold and I can think about cutting it open along properly embedded surfaces. And if I insist that my surface be oriented, I have what's called a partial hierarchy of M. So you start with M0, then remove the neighborhood of S1, have left over, remove a small open neighborhood of S2, look at what you have left over, etc. And it's called a hierarchy if at the end your Mn is just a union of three balls. And Gabai noticed that taut finite depth foliations, so taut is this nice condition about transversals, finite depth we defined, correspond nicely with nice hierarchies of M, where nice here, I need to define for you, means groomed and a groomed sutured manifold hierarchy. So we're now going to weaken the assumption as I promised, and we're going to be thinking about M as being an oriented compact three manifold, and I should have here with corners, and I'll come back to that in a few minutes. But a sutured manifold is just a manifold with extra information about its boundary. So manifold, we're now thinking typically non-empty boundary, though not necessarily. And we are breaking up the boundary. If we think about a boundary component, it might contain some collection of disjoint-oriented simple closed curves, and these are called sutures. So the extra information you have is you begin with your three manifold M, and then gamma is just the disjoint union of regular neighborhoods of the sutures, together with some collection of torus boundary components of boundary M. So A of gamma could be empty, T of gamma could be empty, gamma could be empty, and various combinations of empty, non-empty are possible. So a sutured manifold, you just think about your manifold with some collection of boundary components, and then some collection of simple closed curves. So here is an example. You could think about your manifold as just being the solid torus. And then we see in blue 4 sutures. And the sutures are oriented, the sutures are such that they induce orientations on the complementary pieces of the boundary components. So they bound in the oriented sense subsurfaces, and the subsurfaces are going to alternate on either side of a suture plus minus. And the notation is that R plus of gamma is just the disjoint union of the plus pieces. R minus of gamma is the disjoint union of the minus pieces, and R of gamma is just the union of R plus and R minus. So in this picture, T of gamma is the empty set. A of gamma is just the union of annuli around the sutures, but the sutures capture the information. So at the moment, just got the sutures marked in this picture. So sutured manifold is just, I have a manifold, I look at the boundary components, I see some collection of sutures, possibly empty, I see some collection of torus components, possibly empty, and I take their union because they're for some reason. So sutured manifold. And you think about, we're going to be interested in the complement of a Brown surface. And really, I should have written M is going to be M naught minus one of those I bundle, the interior of one of those I bundle neighborhoods of B. So sorry, there's a typo there. And then the gamma is just going to be the annuli and is just the vertical boundary of N of B. If we had torus boundary components, maybe we would add some in also. And the R plus and minus are just the horizontal boundary of N of B. So if we go back to this regular neighborhood, we can see that the vertical boundary is foliated by these I intervals. And so it's going to be, and everything inside is oriented. So we're going to see a union of annuli, presuming we started in a manifold that was closed. Otherwise, there's something we can say. And the R plus and R minus, well, we can think about case that I guess implicit also was that my branch surface was transversely oriented. So it makes sense that the annuli cut the horizontal boundary into plus pieces and minus pieces. So sutured manifolds arise naturally when you are thinking about branch surfaces. So here's another observation of Gabai, and that's that partial hierarchies give rise to branch surfaces, which in turn, and I should have co-oriented branch surfaces here, which in turn give rise to partial sutured manifold hierarchies. So I can think about just play this traditional or classical decompose along surfaces game. Each of my MIs are manifolds. I cut open along the surfaces. So I can think about just taking the union of all of these surfaces in my manifold. I can think of them as giving me some type of spine. I've just got this disjoint union. And then I can use the co-orientation on the surfaces, or the orientation on the surfaces, to tell me how to smooth this union of surfaces S1 through Sn to a branch surface, and do this inductively. So, for example, if I've just got my S1, my S2 is going to have boundary lying along S1, say, and each of the surfaces are oriented, and we just smooth to a branch surface with double points, as we've shown on the right-hand side there. And B2 is going to be the branch surface that we get from playing this game with S1 and S2. And in general, we've got BK, which we can play by taking the union of the first KSI. And there's only one extra wrinkle that can happen, and that's that if I'm adding a surface SK, it might cross the vertical boundary of the previous branch surface, the branch surface BK minus 1. But in that case, if one's used to playing these games, what one has just created is a triple point, and those purple lines are supposed to keep track of keep track of the del V of the corresponding neighborhood of the branch surface. So there's a cusp, there's a suture that comes in from the front of the page, and then immediately when it hits the red goes up. And then there's one that starts along SJ and SI from the back, corresponding to this cusp. And then it just travels along the red, because if you think about how that red is creating a vertical boundary, it's creating the vertical boundary like this. So there's a well-defined way to go from a hierarchy to a branch surface. We might have started with, really a partial hierarchy, and ended up with a branch surface. It could have been a terrible partial hierarchy, and this could be a terrible branch surface. But whatever. If we have a partial hierarchy, the sutures keep track of extra information. They keep track of the information of this vertical boundary, horizontal boundary decomposition of the branch surface. So at each stage, we have the vertical boundary of the resulting branch surface, and the gamma I is just the regular, or just these vertical annuli. So our new setting is a situation like this, where we're thinking about manifolds, which are the complementary regions of these nice neighborhoods of branch surfaces. So these naturally, if we're keeping track of the differential structure, are three manifolds with corners. And we've got our boundary of our manifold comes equipped with this extra information. Some of the tori are special and included in the sutures. We have this collection of circles, and we have the complementary surfaces to the regular annular neighborhoods of the sutures. And M gamma is a product sutured manifold if it's homeomorphic to a sutured product. So F is just some compact surface with a non-empty boundary, not necessarily connected, and it's a product sutured manifold if M is just the I bundle F cross 0, 1, and the gamma are these annuli boundary of surface cross 0, 1. And M naught gamma or naught is decomposable if there exists such a partial sutured hierarchy where you end up with just a product sutured manifold, something that looks like F cross interval, boundary F cross interval. So this is what we're going to be interested in. We're going to be interested in sutured manifold partial hierarchies. And we have a sutured manifold hierarchy, again, if Mn gamma n, this product, is just a union of product sutured three balls. So a product three ball is just D2 cross I, boundary D2 cross I. And if you think about wanting to use these branch surfaces to describe foliations, what we did this Danjois splitting and then isotope so it lay in a regular I-fibered neighborhood. And at the end of the day, we want to fill up that empty space. So if we have one of these product sutured manifold hierarchies, so we have product three balls, we at least have a hope that we can fill out the complement by just adding D2 cross, just copies of D2, and then hoping that these things continue into the branch surface. So here's an example of a sutured manifold hierarchy. So just starting with this, the three manifold that is the solid torus with the embedded solid torus removed, as shown in the picture. And then the first decomposing surface, S1, is just that pair of pants. And the pair of pants have been drawn in the way, after you've done the smoothing to get the branch surface. So you can see that you're going to have a vertical boundary corresponding to the biggest circle, and that's going to be on the right, and you're going to have two little vertical boundaries corresponding to the little circles, and they're going to be on the left. And if you cut open along this surface, keeping track of the various suture information, you can see the dark red in the second picture. There's a dark red circle on the left, and there are two dark red circles on the right. Those are just keeping track of the sutures, the vertical boundary that we could see in the picture above. And then the next game is just to cut open along an annulus. And if you cut open along the annulus and keep track of the suture information, what you end up with at the end is the picture you have on the bottom right, just a sutured product three ball. So D2 cross I with a single suture. So Gabai's existence argument breaks down into two steps. The first is that, which require me again to give you some definitions. So if M is taut, we know what taut foliations are. We don't yet know what taut sutured manifolds are. Then M has a groomed sutured manifold hierarchy. And I need to tell you what groomed means. And in the other direction, if you have a groomed sutured hierarchy, then you can construct a taut finite depth foliation. So we're interested in taut sutured manifolds. And before I define a taut sutured manifold, I just need to remind you about the Thurston norm. So if I give you a surface, I can look at this chi minus of F, which is just the max of minus the Euler characteristic in 0. And then the Thurston norm is just the minimum chi minus over all surfaces that represent Z. So for Z in second homology, or if you prefer to think in first cohomology. And then the manifold M gamma, the sutured manifold, is taut. The key thing is this first condition, that R of gamma is Thurston norm minimizing. So remember, we have this manifold, we have these sutures, the complement of the sutures give us those subsurfaces R gamma, and you want those all gammas to be Thurston norm minimizing, so to minimize this chi minus in the relative homology where it's M rel gamma, the sutures. And then, we need to have a little bit of cleanup also. So if you're low Euler characteristic, you have to worry about also asking that Q be incompressible. We need M to be irreducible. And then there's this condition that just makes things nicer, that for every component of this sutured manifold, either both R plus and R minus are non-empty, or their union is empty. And so key is this, not immediately clear condition. I mean, the definition is clear, but what it really means. But just have some baby examples. If I give you a knot in S3 and XK is its compact exterior, so we take S3 and we remove an open neighborhood of the knot, then S3 minus this neighborhood of K, and then the boundary of the neighborhood of K is a taut sutured manifold. So in this case, A of gamma is empty, and T of gamma is just that boundary component. A second example would be start with your knot and its exterior and decompose along a minimal genus Seifert surface. Now you're going to have this boundary, which is twice the genus of the minimal genus Seifert surface, and you've got a single suture. And this is going to be an example of something which is a taut sutured manifold. The condition groomed, well, you want both M gamma and M prime gamma to be taut. And then you want the boundary S to interact with the sutures in sort of the cleanest way. So 2 is just there to make sure we don't introduce any dead end components. So not so important for the rest of today's talk. But what we want is that if we look at any component of the complement of the sutures, all we see are properly embedded arcs or parallel, coherently oriented, non-separating simple closed curves. And we want that no collection of arcs of boundary S intersection with these annular sutures is trivial. So we don't just have little arcs that move into the annulus of gamma and pop out on the same side. So groomed key is that M gamma and M prime gamma are both taut, and that S, the boundary of S, lies in a nice position with respect to the sutures. And so Gabai proved that you can always tautly decompose. So if I give you a taut sutured manifold, there's always going to be a surface S, so that if you cut open along S, you end up with something taut. And this can be improved a little bit. So Schallemann showed that you can show that S can be chosen to realize any given non-trivial homology class. And also, if you are in a situation where you don't want to allow yourself to have closed components, which sometimes is the case, then you can pass to a subsurface by just throwing away all the closed surfaces. You've changed probably you've changed your homology class, but you haven't changed the homology class of the boundary in the homology of the boundary. And then step 2 is that you can find a finite sequence of such things. So Gabai's game was to say, oh, look, I can find a sutured manifold hierarchy corresponding to the sutured manifold hierarchy. You can construct foliations. And to show that there's a sutured manifold hierarchy, there were 2 pieces. The step 1, to show that you can always do something. And step 2, showing that you can always make your choices so that the process terminates. And let's see. Okay, so let me just really quickly say that for the step 1, showing that you can always proceed, it really is just a Thurston normal game. And both Gabai Gabay originally used this, and so did Charlemagne in his modification. So just that, you've got these edges, and if you're close enough to, if you lie on the, sorry, I shouldn't say edges, dimension is wrong, but that you can, the Thurston norm ball is of the form V cross B, where V is a subspace of Rn, and P is a compact convex polyhedron. So that just means, since we're a compact convex polyhedron, we've got linearity if we lie close enough to something nice. And so the game in showing tautness is to show that R of gamma minus realizes the minimal Thurston norm, and R gamma minus is just the double curve sum of S and the previous R gamma. And the previous R gamma, by assumption, is Thurston norm minimizing. So you're in a setup where you can take advantage of this game, replace S by S double curve sum with some number of copies of these R gamma, and throw yourself into this lemma to show that once you've taken enough of the R gamma, you have something which is Thurston norm minimizing. And maybe I shouldn't really, let me not say more. So Gabay and Charlemagne then have a next step, but it really is just a Thurston norm game that you can replace S staying in the same homology class in H2 of M boundary M by doing this double curve sum game with something is Thurston norm minimizing. Okay, finiteness. So finiteness, we can relate back again to the classical theory. So the classical theory told us, well, using triangulations of your three manifold, that if you have a partial hierarchy where you're only allowed to cut open along incompressible and boundary incompressible surfaces, then there's a bound on the length of the partial hierarchy. And when I was in grad school, I learned that there are infinite surfaces if you allow there are infinite such partial hierarchies if you allow your surfaces to be boundary compressible. And so for a long time, I was kind of scared of boundary compressible surfaces as being terrible things, but they're actually not. And then Gödel has this really nice result that there are examples of taut sutured handle bodies. So M is a handle body, and it's a suit, but you have the sutured manifold with no taut disk decomposition. So this means that if you have a taut decomposing surface, you have to make choices which are boundary compressible. So in the sutured manifold hierarchy game, you have to allow yourself to cut open along incompressible and boundary compressible things. So you can't just immediately throw back to this result of finiteness. And in fact, Jaco shows you could have infinite. But with a minor little toggle, you've got a really similar result. So if your condition, instead of being boundary incompressible, is that the surfaces are not homologous to unions of disks, you can show that you have a bound again. And so that means that we have finiteness if our goal is to get to a handle body. So the corollary, which we care about right now, is that there's a finite sequence of groomed sutured manifold decompositions that end you with a taut sutured handle body. And so we can restrict attention to taut sutured handle bodies. So taut sutured handle bodies are easy to think about. The handle body part is easy to think about. And here I've got some purple lines, which are just indicating there are sutures running around this handle body. Just think about your favorite, complicated collection of curves that separate the boundary of the handle body, that's surface, into R plus and R minus regions. And just choose some handle body decomposition. So some collection of G disks that cut the handle body into a 3-ball. And now the game is, again, the goal here is finiteness. At each step, we can cut. And the game is to say, if we start with a taut sutured handle body, there's a bound on the number of cuttings we can do, before we end up with a product sutured handle body. And here the game is just look at how these surfaces intersect these decomposing disks. And an Euler argument, you know that there's a bound on the number of non-diagon complementary regions in each of the DMs. So you keep cutting, cutting, cutting. At some point, you can only introduce digons. So this corresponds to you have reached the point where you have a product sutured manifold, a product sutured handle body. So something that just looks like surface cross I. And then you can cut open along what are called product disks. And those are things we know always behave well. If you cut open along a product disk, you start with something taut, you have something taut, and a product handle body, certainly you can just cut open along you can cut open, you've got F cross I, just choose, some collection of arcs in the surface that cut to a disk and choose the arcs cross I to get to the union of product three balls. And so for the final piece of the step, Gabbai said, hey, if you start with a groomed sutured manifold hierarchy, you know you have a taut depth foliation. And the construction is again pretty straightforward in this forward version. So you can think about cutting open. Let's think about what happens. So again, inductively, the game is to inductively set things up. So your first leaf is just the first cutting surface. And then at an induction stage, you're cutting open along an Si+1. And you look at how it intersects the boundary of the manifold you've created up to this point by the cuttings. And then you can take copies of the boundary. And so you can think about, maybe think about this as, again, Dangerois blow-up game. You can just take 0 cross, well, I guess compact boundaries, and delete that comment. So we have 0 cross 1/n copies. And then we can just do, again, this oriented surface cut and paste. And so if we just look at this slice, one dimension lower, we can get this spiraling picture. And Larry will be giving much more careful descriptions of ways to do this. So looking in the bottom line, there's an example where we're looking at a boundary component of Si+1 that misses the sutures. And so in this case, you just take copies of the boundary MI, and as long as your interaction with the sutures is nice enough, you can play the game analogous to the one dimension lower one above. So what's a little more interesting is what you do when your surface cuts across the suture. And in this case, because of the technical pieces in the definition of groomed, you know that you can always find this properly embedded ray cross 0, 1 in the complement of the foliation you've constructed thus far. Attach that to your surface, and now you have this copy of where you play again this infinite cut and paste game to get a foliation at that step. So probably that's a little too quick, but it really is. It really is this easy because of having set up the definitions correctly. So thank you very much, and happy birthday, Paul.
So, are there any questions? Well, it's far from my expertise, but I'm just curious if you're following a construction that takes infinite cutting and paste. So it's not clear to me what do you get by this process?
So as in this top picture on this slide that I'm showing right here. So let's see if I can.
Yeah, that one.
Let's see. Oh, I don't know how to draw. Yes. So, so are you happy if you think one dimension lower? So if I gave you a circle,
Sure.
and then I gave you the circle cross, and you had sort of the circle cross. I have the cross 0, which is, I think of as the original one, and then I've got circles that are limiting on this circle. And then I do this cut and paste. So I've got at each place where I have an intersection, things are oriented. So I know the oriented cut and paste tells me to replace, say, this crossing with something like this. I don't know if you can see my fingers and if they make sense.
Yeah, I can see your fingers.
So you do that infinitely often. You know, if you think about your 1 over n, each 1 over n has a little open interval where you can do this. And so you're going to get this picture on the right-hand side where you started with your blue going in. You did this oriented cut and paste, which picked up a copy of the circle that then crashed into the next intersection, that crossed into the next intersection. So you're going to have this spiraling. You're going to have this limiting process where the resulting leaf, let's call it Si plus 1 prime, has the copy of boundary Mi in its closure.
Okay.
I don't know if that helped at all, but
No,
you know, locally you're just doing the cut and paste. You have a little open neighborhood where you have space to do it, and everything's well defined. And you just do that everywhere.
Okay, thank you. Are there any more questions? If not, so let's thank Rachel again. So we resume at 11:10.